So for the next recording, we are going to do the area under the curve y equals x squared plus 3 from x equals 1 to x equals 5 using n rectangles and the right-hand endpoint method. So the first thing we'll do is we'll look at sketching in the rectangles so that in such a way that the right hand portion of the rectangle is hitting the curve. And then we will label the numbers k equals 1, 2, 3, 4, etc. all the way up till our last rectangle. To calculate the base of each rectangle, the highest value of the interval, in this case 5, minus the lowest x value in the interval, in this case 1, divided by the number of rectangles. In this case we are using n rectangles. So the base of each rectangle can be found by 5 minus 1 divided by n, which gives us 4 over n. So the width of each rectangle, the delta x, or the base of each rectangle, can be given as 4 over x. Next we'll fill in our little chart. K equals 1, 2, 3, and 4. This will be used to translate from x's into k's when we write our sigma notation evaluation. So for the right hand portion of the first rectangle, we're looking at this part of the rectangle would be the part that would hit the curve y equals x squared plus 3. So that appears to be at an x value of 1 plus whatever the width of one rectangle is. Now the width of each rectangle can vary depending on the number of rectangles we use, which would be n. So in this case we'll write it generically that the x value we'll plug in for the first rectangle would be 1 plus 4 over n. To use the height of the second rectangle, you have to move over from x equals 1, 2 widths, and right over there is the height that you should be looking for. So that would be 1 plus 2 times 4 over n, and for the third rectangle it would be 3 widths, would be 1 plus 3 times 4 over n. Following this pattern, we should be able to get an equation for what x equals. In each case, if you notice, we're going to do 1 plus some value. In the first part, we're doing 1 4 over n when k was equal to 1. The second trial, when k equals 2, we're doing 2 times 4 over n. When we're doing the third trial, it's 3 times 4 over n. So logically, it should follow that the equation would be 1 plus k times 4 over n. Moving the 4 times the k to the top of the fraction gives us 1 plus 4k over n. So let's separate that from the rest of our work. Start by writing our sigma equation. K equals 1 to n of the area of the kth rectangle, which is equal to the base of the kth rectangle times the height. The base of each rectangle we know is given by 4 over n, as found earlier. The height we know we're going to find by plugging into the equation x squared plus 3. However, we don't want x's, we want k's. So we have to use the translation down here, x equals 1 plus 4k over n. So rewrite the expression we have here, and the only thing missing is my x value. Well, let's put in the x value. 1 plus 4k over n. Now we have to do some algebraic simplification. First, square the 1 plus 4k over n. So that should be 1 squared plus 2 times 1 times 4k over n plus 4k over n quantity squared. That's just using the formula a plus b quantity squared equals a squared plus 2ab plus b squared. So squaring this out, we'll still have the 4 over n as the base. 1 plus 8k over n plus 16k squared over n squared, and of course we still have the plus 3 at the end. Simplifying further, we can distribute the 16 over n. Well, let's see, what did I do? I have 4 over n times 1 plus 3, which is also 4. So 4 times 4 over n is my 16n. 4 times 8k is 32k. N times n is n squared. And lastly, 4n times 16k squared over n squared is 64k squared over n cubed. Now we have each of these sums individually. So what I want to do is I want to put each part into its own sigma. So sigma 16 over n, sigma 32n squared over n squared times sigma k, and 64 over n cubed sigma k squared. So the idea here is to treat anything that has a k as a variable. So the k's are the variable. Anything that does not have a k, like 16 over n, 32 over n squared, 64 over n to the third, those are our constants. At this point, we're ready to apply the formulas. For this one here, this is sigma constant. So we're going to get 16 over n times n, and you notice the n's will cancel out. For the middle term, this is sigma k. Formula for k, n times n plus 1 divided by 2. That's still multiplied by the coefficient 32 over n squared. At this point, the 32 cancels with the 2. The n squared becomes n to the first, and that cancels with the n up here. And the formula for k squared, of course, n plus 1, 2n plus 1 over 6. You still have that times the 64 over n to the third. Canceling the 64 with the 6 gives you 32 over 3. The n to the third becomes n to the second. The n cancels out as well. Simplifying the first term is 16. The second term simplifies. When you distribute the 16, becomes 16n plus 16 on top and on the bottom. And the third term, when you multiply out n plus 1 times 2n plus 1, you get 2n squared plus 3n plus 1. We still have the 32 on the top and the 3n squared on the bottom. Further simplifying gives me the 16 that I had here. 16n over n is going to become another 16. And this part, 16 over n, becomes 16 over n. The 32 times 2n squared is 64n squared. Divided by 3n squared gives you 64 over 3. Distributing the 32 to the 3, n, would give us 96n. Divided by 3 is 32. And the n squared on the bottom leaves me, the n cancel with the n squared, leaving me n on the bottom. And 32 times 1 is 32, divided by the 3n squared. So the 3n squared gets divided into each term individually after the distribution has been done. Combining like terms, regular numbers, 16 and 16. Numbers with just n in the bottom, 16 and 32. And then with the n squared, 32 over 3n squared. I neglected to say 64 over 3 is also a regular number. So it's 16, 16, and 64 thirds. And then the 16n and the 32 over n combined, and the 32 over 3n squared combined. Leaving us with 160 over 3 plus 48 over n plus 32 over 3n squared. Now that would be the final answer if you just said n rectangles. So that is the approximate area under the curve. Now we've done RRAMm. So if you've done an RRAMm, you should get the same exact answer that you did before. So let's say, for example, if you did an RRAMm 4, you should get the same exact value as if you plugged 4 into this equation. So let's see what we would get here from an RRAMm 4. I'm not getting, oh, that's because my pen is on white. That doesn't work. So let's go up here, plug in n equals 4. I have 160 over 3 plus 48 divided by 4 plus 32 divided by 3 times 4 squared. So that would be an RRAMm 4. So if our equation's right, it should work out. So I have 160 divided by 3 plus 48 divided by 4 plus, I'm just going to do this all out on my calculator here, 32, and you can do the same, divided by parentheses 3 times 4 squared, close the parentheses around there, and I'm getting 66. So hopefully when we did our RRAMm 4, we had an answer of 66. Now the next part of this would be to do the exact area. Now the exact area is going to happen when we let the number of rectangles get larger and larger and larger and larger. Because what happens when the number of rectangles gets larger is the little spacing in between the rectangles and the curve gets smaller and smaller and smaller. So if we say that the limit as the number of rectangles n goes to infinity of this expression, 160 over 3 plus 48 over n plus 32 over 3n squared, that should give us the exact area. Well, if the limit as n goes to infinity is applied here, remember that means the intended y value or intended answer. 48 divided by an infinite number is going to go to 0. And some number divided by n squared is going to go to 0. So those would just drop out of the equation, meaning your exact area would be 160 divided by 3, which turns out to be 53.3 repeating. So that would be how you could find the exact area under the curve using n rectangles. Thank you.